Hi, AP Chemistry. We are looking at Unit 2 in this video. All right, so we'll be reviewing Unit 2. Unit 2 looks at molecular and ionic compound structure and properties. All right, so the two enduring understandings we'll see. Atoms or ions bond due to interactions between them, forming molecules. And molecular compounds are arranged based on Lewis diagrams and valence shell electron pair repulsion, VSEPR theory. All right, so the first thing we want to think about is electronegativity. All right, we need electronegativity to make sense of the type of bond that's going to form. All right, and we should remember the trend for it, right? So electronegativity increases to the right in any given period. And that occurs because we get more protons in the nucleus, so we get a stronger Z effective, the effective nuclear charge. And as we get more protons in the middle, the atom is able to attract electrons easier, so that's across a period. It decreases as you go down any given group, all right? And the electronegativity decreases because the valence shell gets further away from the nucleus. Any given column on the periodic table has the same effective nuclear charge because of the inner shell electrons shielding. So any element in group 15, for example, the effective nuclear charge is going to be 5. All right, doesn't matter which period it's in. So that's why it decreases. All right, so that's something important. So again, as we look across a period, effective nuclear charge increases by 1. All right, and so that's why our halogens are so strong, and our noble gases will not have any electronegativity. All right, they are not going to be attracting electrons because they have full shells. All right, and just again, when we're thinking down the periodic table, even though we get more protons in the nucleus, there is more shielding. So the whole point is that the outer electron is getting further away. All right, so the larger effective nuclear charge has to do with Coulomb's law, right? So you're getting a bigger charge, so we're going to have a stronger attraction. And the valence electrons being further away also goes back to Coulomb's law, because now we have a larger distance, and in Coulomb's law we divide by the distance, so it gets further away. It's not as strong. All right, so when we're looking at a non-polar bond, these are two atoms with very similar electronegativity. All right, the easiest is when we have two of the exact same atom. So here we have an H2 molecule. Both hydrogens have identical electronegativity. So what we end up seeing is the electron gets shared. There's an overlap, all right, but no side is favored. So the electrons don't spend more time on any particular side. So it's distributed very evenly throughout. So that's the non-polar covalent bond. All right, it can be a difference that's slightly different electronegativity. The carbon-hydrogen bond, all right, is a very good example. Carbon has an electronegativity of 2.4, I believe, and hydrogen is 2.1. So their difference in electronegativity is 0.3, which is very low. So every carbon-hydrogen bond is non-polar. So it doesn't have to be 0, all right, but it should be less than 0.4, around there. All right, so the whole study of organic molecules, all of those carbon-hydrogen bonds, those are always non-polar covalent bonds. All right, so now we have the polar covalent bond, and this is an electronegativity typically between 0.4 and 1.8, that difference in electronegativity. The carbon-oxygen bond is a good example. Carbon has a bond of 3.5, oxygen's 3.5, carbon is 2.5. That difference is 1.0. So a couple of things happen in the polar covalent bond. The atom with a higher electronegativity will develop a partial negative charge. All right, and that happens because the electron cloud actually spends more time around the oxygen. So if we think of those electron clouds as the distribution of probabilities, well, the probability that it's near the oxygen and not the carbon is greater. So it's going to have more time spent there. All right. Now, in single bonds, greater differences in electronegativity lead to greater bond dipoles. All right. So that dipole does have its own kind of scale. We can get a more significant, a bigger dipole, or we could have a relatively small dipole. So it's important to think of it as like a sliding scale. All right. And all polar bonds have some ionic character, and the difference between ionic and covalent bonding is not distinct, but rather a continuum. So that's a really good idea, this idea of a continuum. As a bond becomes more polar, we could think of it as being more ionic in nature. All right, just some things to note with the polar covalent bond. We always want to represent it in two different ways. One is the arrow. All right, when we have a dipole, we like to draw this arrow, and the arrow is showing the direction the electrons are moving. So hydrogen's electron is being pulled towards chlorine, so that's why the arrow is pointed towards the Cl. The other thing we can use is this Greek symbol. It represents a partial charge. So we get a partial positive for hydrogen and a partial negative by chlorine. All right, but so we get these partial charges, both important ways to represent polar covalent bonds. And then you'll see them again in Unit 3 when we look at intermolecular forces. So we should be very comfortable with these symbols. We should include it whenever we're drawing a polar bond. All right, and just something to think about with this whole idea of continuum. I found this picture, I thought was pretty interesting, the way that as we move through different elements, we could move from metallic bonding to more ionic in nature, and then the ionic can kind of move towards covalent. So we have this idea of percent ionic character, all right? It's based on the strength of the dipoles. So low dipoles have like a 0% ionic character. Really strong dipoles have a high percent. So just again, this idea of a continuum, a covalent compound can be described as like an ionic compound. So that's not unheard of. So it's something to keep in mind. But we should remember the difference in electronegativity, it's not everything. All right, it's a really good starting place to determine the type of bond we're going to have. All right. In that previous slide in this review, I used the differences of 0.4 as the boundary between nonpolar and polar, and 1.8 as the boundary between polar and ionic. But that's relative, that's arbitrary, all right? If you're in a college lecture, they might use different numbers. They might say 0.5, they might say 1.7, all right? Something to keep in mind. Anytime you're looking at a compound, think about its structure, its makeup. If it is a metal and a non-metal, that is an ionic compound. All right, there's a give-take there with the valence electrons. It doesn't matter if the electronegativity is less than 1.8. All right, there are some really weak ionic compounds. And if it's two non-metals, it's definitely not going to be an ionic compound. It might have a high ionic percentage. It might act like an ionic compound, but it won't be one. A good example of that would be like HF. All right, HF has a really big electronegativity difference. Sometimes people miscategorize it as ionic. That's just a very big polar bond, right? A very big dipole moment. So that's going to be important. So just keep in mind, it is the makeup of the compound. So you should always be thinking, is it a metal and a non-metal, or two non-metals? All right, now metallic solids should be pretty easy. All right, their valence electrons are called delocalized. So here we have this picture. All of the plus signs represent the nucleus of the metal, and their electrons are delocalized so they can move about. They almost kind of swarm around. All right, and this gives metals those very characteristic properties they have. They conduct electricity easily because of the delocalized electrons' ability to move. They also conduct heat easily, again, because of that electronic structure and because the electrons can freely move about. All right. Now, we sometimes use these potential energy versus distance diagrams to understand a bond. All right. So what happens in these diagrams? All right. The y-axis is potential energy. So chemical compounds are formed. These bonds form because the bond is supposedly has less potential energy than the two atoms in their unbonded form. So we see that. We want that dip. We want the lowest possible potential energy. So when two atoms are too far apart, there's no overlap, right? There's no attraction between their two nuclei. But as they're brought closer together, Um, the nucleus of one atom is able to attract the electrons from the other atom and vice versa. So as they come closer together, that attraction starts happening both ways, and it'll reach kind of this perfect distance where there's overlap and it has less potential energy. Now, if we try to push them even closer together, they start getting too close where the nuclei of each atom starts repelling apart. So we do get this equilibrium bond length, all right, too far apart and there's no attraction, too close and they repel and they'll fly away. All right, I believe we saw a PhET simulator at one point in the year with this. There is one if you wanted to look it up where you can kind of slide them back and forth and see what happens. And if you force the atoms too close, they shoot apart. All right, so we want that equilibrium spot, and that kind of governs it. Now, bond length is measured between two atoms. What they do is what we're trying to find in the bond length is the distance from one nuclei to another. Sometimes they take the entire distance and then divide it in half, right? Assuming that that's just half of the molecule. But bond length, it's influenced by both the size of the atom's core and the bond order. All right, so bond order just means single bond, double bond, or triple bond. And then the size of the atom, think back, we've seen the trends for atomic radius. How many shells do we have and how tightly held is that shell? All right, bond length was used. It was 2019. It was part of an open-ended question. So the molecular formulas of diatomic bromine, chlorine, fluorine, and iodine are written below. Circle the formula of the molecule that has the longest bond length. Justify your answer in terms of atomic structure. All right. This is a one-point question, but it's a really easy one. The answer is iodine. The iodine atom is the biggest of these four atoms. All right, so if it's a big atom, its bond length is going to be from its nuclei to its outermost electron. So if we have two iodines, they're going to be really far apart relative to two fluorines, which are significantly smaller atoms. All right, and then bond order. A single bond is always going to be longer than a double bond, and the triple bond is always going to be the shortest. Doesn't matter what they are, right? If we're comparing just carbon-carbon, this is nice and easy because they're all the same. So just keep in mind, as we increase the bond order, the strength of the bond increases, there's more connections, there's more overlap, and the length will decrease. All right, now we can use Coulomb's law when we're looking at an ionic compound because we're looking at the lattice. All right, so the lattice is the alternating pattern of positives and negatives. So positive ion, negative ion, back and forth. Now Coulomb's law, it's between any 2 points. So the two ions are going to represent our 2 points. And again, we know for Coulomb's law, Q1 times Q2 divided by R. All right, so the bigger the ion is, that means it's going to physically push its outer edge. So the bigger atoms will tend to have weaker lattice energy. All right, the really small atoms, they're able to get really close to each other in the lattice. They're going to have the greater Coulombic attraction, so the greater lattice energy. Now, the other thing we can keep in mind, that's just R, that's the distance, is the charge. So a +1 ion, that's going to be its charge. So a +2 or a +3 ion is going to be even greater than a +1 ion. All right, so we want to think about the type of ion. You know, based on its charge, as the charge gets bigger, its lattice energy will get bigger. All right, and then we still want to keep in mind the idea of size. Something to remember, anions, when they form from their original non-metal, anions radius is actually bigger than the non-ionic non-metal, and cation radii are actually smaller than the element that they start from. All right, but again, this is typically what we want to think of when we go down a group. As we go down a group, we add more shells, so the atoms get bigger. So if we're comparing magnesium to barium, magnesium is going to have a higher lattice energy because they have the same charge of +2, but magnesium is significantly smaller than barium. All right, and the cation and anion in the ionic crystal, they're arranged in such a way, and it's three-dimensional, but they're arranged in such a way to try to maximize the attractions and minimize the repulsions. So if we take the positive sodium ion, it's going to have fluoride ions surrounding it. right? So the idea is there's attraction in all of these directions. We don't want a sodium directly next to another sodium. So they're kind of spaced out in that way. They're on those diagonals. This is why ionic compounds are said to be brittle. If you were to push the lattice over just one, it'll completely shear. All right. And this is a boundary. This is something that is not required for the AP exam. There are several different types of crystalline structures that these lattices can take. You don't need to know them. All right. So you don't have to worry about body centered versus face centered versus cubic versus rhombic. All right. This is stuff that, if you're really interested in, you'll develop in college in, a solid state chemistry class or something like that. But it is something, an X-ray crystallography class, but it is something that you do not need for the AP curriculum. All right, so do not worry about that. It used to be there in like the really old curriculum, and it's one of the topics that's been taken out. So you don't have to worry about that. They will be nice to you. Everything will be kind of the same, repeating 1, 1, 1, 1. So you don't have to worry about all these different structures. All right, now metallic bonding, it is called the sea of electrons, all right, because of the delocalized valence electrons. And again, these only represent valence electrons. All of these positive charges do include the inner core electrons. So not all of the electrons are moving about, just the valence electrons. But anyway, they're free to move about, and so they can kind of slide past each other. So it came up with this term sea of electrons, and it does describe the properties of metals beyond just heating and conducting electricity and conducting heat. So metals are said to be malleable, which means we can we can subject them to a lot of stress and they'll deform, but they won't break. So what's happening there is the cores of all these atoms, they're able to slide past each other because the electrons can move out of the way. So if you were to hit a piece of metal with a hammer, you can deform it, but you won't break it, right? They're still touching each other. And metals are ductile, which means it can be stretched into wire. Copper is used for wire because it's really good at connecting electricity, but also because it's so ductile. It can be stretched into this nice thin wire. And that's, again, the sea of electrons. The electrons are able to slide past each other, so we can keep all of those copper atom nuclei with its inner shell electrons together, and the valence electrons can slide about so they can keep it all together. All right, now we do get alloys. The first type of alloy we're going to mention are interstitial alloys. All right, this is where you take a pure metal and then you have something else inside of it, in those gaps with a significantly smaller radius. So the example here would be steel, which is typically iron atoms, which iron has a large radius, with small carbons, and it's interspersed between the iron atoms, right? The interstitial alloy, steel's really strong because the iron atoms can't slide past each other anymore, all right? They are being blocked by those small carbon atoms, and that's what makes it so much stronger. Something to note with an interstitial alloy, this is a solution, a homogeneous mixture, all right? So the main metal would be the solvent, and whatever the interstitial alloy, whatever the small radii that's being added, that would be your solute, and it's being dissolved within. All right, and then we can also get a substitutional alloy. This is where we have two different metals that have very similar radii. All right, so a good example would be brass, which is a combination of zinc and copper. They're about the same size. Sterling silver, different versions of that can be combinations of silver and gold. All right, so you can get like that rose gold, all different things like that. You can get combinations. Those are similar in size, so they can be substituted between each other. All right, so again, substitutional, you're looking for something with the same radii. Interstitial, it's a much smaller radii. And you can get certain alloys that have both. They're substitutional and interstitial, so that is allowed. So it's something to be wary of. So now we're going to look at Lewis diagrams. All right, this is an important topic. You've drawn a ton of Lewis diagrams this year. You've seen AP questions where you're asked to fill in a Lewis diagram or you're given a Lewis diagram. The first thing to note, Lewis diagrams are based on valence electrons. So you need to know the valence electrons. You should know that based on the group number on the periodic table, right? Groups 1, 2, and then 13 through 18, 1, 2, and then 3 through 8. All right. We draw 4 separate before we start doubling them up, and we call a pair of electrons a lone pair. A pair of electrons typically does not bond. All right, not to say that it cannot happen, but typically it doesn't. It won't happen in our second period, so you don't have to worry about that. All right, so the easy Lewis diagrams are for ionic compounds. In an ionic compound, the metal loses its electrons. Those electrons are gained by the nonmetal. So in our example here, we have magnesium donating its 2 electrons to an oxygen. 2 things to note. You want to draw ions always in brackets with the charge outside. The magnesium doesn't have any electrons around it now, and that is the correct way of representing a cation. Cation should have no valence electrons. It has lost its valence electrons because its inner shell is filled. Right? That's why their radii get smaller for the cations. For the oxygen, it now has more valence electrons than it would normally have, all right, and it has the charge of 2 minus. In this example, one thing I don't like, the calcium should be in brackets, but you might need multiple of a particular atom. So in calcium chloride, calcium's going to donate 2 electrons. It needs 2 separate chlorine atoms to gain. Each is going to gain 1 of those valence electrons, but since calcium gives up 2 electrons, it needs 2 chlorines there. All right, and that is how we come up with the chemical formula for calcium chloride, CaCl2. All right, so that's our ionic compounds. Now, I like this honk 1, 2, 3, 4 rule for hydrogen, oxygen, nitrogen, and carbon. They form 1 covalent, 2 covalent, 3 covalent, and 4 covalent bonds respectively. So honk 1, 2, 3, 4. It works really well if you're only using those 4 elements. As we start adding more elements, sometimes it falls apart. Something that this doesn't mention, oxygen always has 2 lone pairs. It has 6 valence electrons. 2 of them are paired up. We call those lone pairs. 2 of them are unpaired, which is why it forms the 2 bonds, and nitrogen always has 1 lone pair. So something that this rule doesn't represent. But when we start to draw these structures, every hydrogen is only forming 1 bond. Every carbon is forming 4 bonds. It can be a double bond. That counts as 2, 3, 4. And every oxygen is forming only 2 bonds. So that honk 1, 2, 3, 4 rule, it's really good. It's really good when we're drawing organic structures. But it's not the be-all, end-all, but it's certainly something, if we only have these elements, we can work quickly. Nitrogen will form 3 bonds. Here it's being shown bonding to 2 carbons and 1 hydrogen. All right. Something I wanted to point out, I do not like this representation where we use pairs of dots to represent the bonds. I have seen it in different ways. I've seen so like our triple bond here between the 2 carbons, it's 3 pairs of dots. They're lined up. Sometimes I've seen them stacked on top of each other. Generally speaking, I think you should always stick with drawing lines for your chemical bonds. I don't think the pairs of electrons are that great. On the AP exam, they will say that graders will accept either, but I think it's easier for the grader to see your work if you draw the lines. So I am not going to recommend that you draw bonds in this fashion. All right. Now, there's a couple of steps to drawing Lewis dot structures. So a simple way to draw them would be to arrange the atoms. Our central atom typically has the lower electronegativity. And when you're looking at a chemical formula, if you see only one of a particular element, that's usually a good indicator it's going to be central. Add up the valence electrons of all the atoms. You kind of want to take stock, figure out what's going on. Remember with our ions, if it's a positive ion, that means we've lost that many electrons. So if it's +1 ion, you would subtract an electron. If it is a negative polyatomic ion, whatever the negative charge is, you have to add in those extra electrons. So if something's -2 charged, it has 2 extra electrons. If it's -3, it has 3 extra electrons because negative polyatomic ions have gained electrons. All right, so then you would draw single bonds to attach all of the elements. Each single bond counts as 2 electrons. And what would end up happening, typically, you would then go back and draw octets to satisfy the octet rule. Give every element an octet. Hydrogen is the only exception. Hydrogen does not need an octet. But the octet rule is not a great rule because it can easily be violated. So I just wanted to give you an example here. If we were drawing carbon dioxide, which we're familiar with, CO2, if I count it up, carbon has 4 valence electrons, each oxygen has 6, so that gives me a total of 16 valence electrons. I would put carbon in the middle, it's less electronegative, also there's only one of them. I would attach the 2 oxygens. I would give every element an octet and then recount. All right, each bond counts as 2 valence electrons, and then all of the lone pairs gets me to a total of 20 valence electrons. Now that's 4 more than I have. So we're going to use that trick where you can remove 2 adjacent lone pairs and replace it with a double bond, and that reduces your number of valence electrons by 2. So if I were to remove these 2 lone pairs, I make a double bond, I now have 18 valence electrons, I'm close, I can do it again on the other side, so we end up with the structure that we should be very familiar with, O double bonded to carbon, double bonded to another oxygen with the proper number of valence electrons. So the octet rule, it's a good rule to give every element besides hydrogen an octet, but you will have to recount afterwards. And if you're using too many electrons, you use this double bond trick. If you give every element an octet and you still have leftover electrons, you counted up the total number of electrons at the beginning of the problem, and you have extra, you're just going to add lone pairs to the central atom. All right. You may feel like this is violating the octet rule. You are. And the octet rule is not a great rule. So have no fear if you have to violate that octet rule. Just as a thing I want to mention, boron always violates the octet rule because it never has 8 valence electrons. It only gets up to 6. All right. And something again I want to point out, if you have a polyatomic ion, you're going to put it in the brackets. Here we have NH4, and it's a positive 1 charge. And when we went to count the electrons, nitrogen has 5 valence electrons, hydrogen each 1. That gets us to 9. But then we subtract 1 because it's positive charged. And each bond counts as 2. So 2, 4, 6, 8. This is perfect. All right. And NO3, here's an example where we had to put in a lone pair. We had to remove 2 lone pairs from nitrogen and oxygen to get our proper number of electrons. We get the double bond, and we put the charge outside of the brackets. Now, could we have put the double bond on the bottom right or the bottom left? Absolutely. All right, this leads us to the idea of resonance. So typically, whenever we have double bonds, if they could have been in multiple spots, we kind of think of the double bond as being in all of those spots at once. So here we have the carbonate ion. The double bond could be up top, lower left, lower right. We draw all 3 of them. We show that they're all equivalent to each other, right? When we think about resonance structures, we are not moving any of the atoms. We are only moving the electrons, right? So the double bond and a lone pair move. So it's the same physical structure, it's just how it's being held together electronically. And so one thing we're able to do, we can make this composite diagram where anytime we have a double bond, we would show the bond, and the second bond we would show as a dash, and we do not have to include the lone pair, right? That would have moved out of the way. And we can end up kind of dividing these bonds. So the formal charges, which will be in another slide, kind of change. So you can come back to this if you're worried about that. All right, now formal charge. Formal charge, when we have neutral molecules, formal charge typically should always be 0 for elements. It's based on the number of valence electrons the atom has, and then how many it's being represented with. So here in this example, we have carbon dioxide. This central carbon, it has 4 valence electrons, and it's got 2 double bonds. So each bond, it's half of the electrons, because it's 2 electrons total. One of the electrons goes to the one atom, the other comes from the other atom, right? So we typically like to take the bond and divide it in half. So we have 4 bonds, that would be 8 valence electrons, but we divide it in half, 4. So carbon's shown with 4, it's using 4, its formal charge is 0. And the oxygens, it's the same thing. They're shown with 6 valence electrons, and they are using 6, so 6 minus 6 is 0. And again, counting the electrons on the oxygen, 2 bonds. Now, each bond includes 2 electrons, so that's 4 total. But we divide it in half, so that's 2 plus 2 from the lone pairs gets us the 6. All right, so again, formal charge, what it should have minus what it has. Lone pair electrons plus half the number of bonded electrons. So formal charge helps us understand what's going on in a structure, and it helps us critique if a structure is good or not. So here we have 3 possibilities for NCS. These are not resonance because the carbon and nitrogen are not in the same place in all of them, right? So it's kind of like we're trying out all 3 elements for the central atom. But when we look at the formal charge on the left, we get a formal charge of -1 on the nitrogen, 0 for the other 2 elements. All right, this middle one, we get -2 plus 1 and 0. And the one on the right, we get -2 plus 2 and -1. And again, all of these are being assigned by counting up the number of valence electrons the element should have, and then subtracting what it's being shown as having, which is, again, lone pairs plus half the number of bonded electrons. Now, the formal charge should add up to the charge of the polyatomic ion. So since it's a -1 anion, it should equal -1. And all 3 do, so that's good. But we like structures that have the lowest possible formal charges. All right, we do not like a formal charge of -2, and we certainly don't like -3 and beyond or +3 and beyond. So this structure here, because of its formal charge, is going to be the best structure. So it's something we can use to make sense of a structure and to compare if something is good or not. All right, again, the formal charge, typically if we have resonance structures, the formal charge can move between them. So both of these are in resonance because it's the correct number. None of the atoms are moving. So each oxygen takes a different turn being -1. So what we can end up doing is the formal charge would be -1/2 in the composite. In the composite resonance structure, it would be the formal charge divided by the number of structures. All right. Something to note with Lewis structures, they are lacking at times. One of their biggest downfalls is when we have an odd number of valence electrons. In organic chemistry, we call these radicals. All right. Sometimes it happens. Carbon could be a radical, oxygen could be a radical, chlorine, and it's an atom that doesn't have all paired electrons. All right. So this is kind of a shortcoming. So again, with Lewis structures, oftentimes you can get frustrated because there's a lot of exceptions. Just keep in mind, they're not perfect. Formal charge is a good way of making sense of Lewis structures. The octet rule is not something that is adhered to as much as maybe a middle school teacher would have you think it is. All right, so for the octet rule, it really only works for the second row elements, and not even all of them, like boron and beryllium already violated because they have less. So the octet rule, it kind of guides us in placing the electrons, but it is not a hard and fast rule. All right, so the last piece of this unit had to do with the VSEPR model, right? The valence shell electron pair repulsion. All right, and so what this does, it thinks about the Coulombic repulsions between electrons. Electrons do not like each other. So the electron clouds, or their orbitals, right? We can use those 2 words interchangeably. Those clouds don't want to overlap with each other. They push each other out of the way. So if we have 2 of those clouds or 2 of those orbitals, they're going to naturally find this linear shape so that they can be as far away from each other as possible. When we have 3 of the orbitals, they're going to form this trigonal planar shape, and that allows them to be as spaced out as possible. And 4 of them naturally form the tetrahedral shape. All 3 of these shapes you could make at home with just balloons. If you tie 2 balloons together, it'll naturally form a line. If you tie 3 balloons together in the middle, it'll form that trigonal plane, right? And again, plane, it's going to be in the same plane, so it's flat. And if you tie 4 balloons together, it'll make that tetrahedral shape. And the tetrahedral shape, if you have ever used a 4-sided die, that 4-sided die is also a tetrahedral shape. All right. Now, based on that, we can look at the central atom. We can come up with all these different types of shapes. So linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, trigonal bipyramidal, octahedral. So we get a lot of these different types of shapes. That is the VSEPR theory, the type of shape around a central atom, and we can predict it. All right. One of the ways we predict it is these charts we've learned. All right. We can come up with the structure around the central atom. We've done AX, AX2, AX3, AX4, X representing a bonded group. We can do AX3E, where E represents the lone pairs. So we've been through these charts. They explain the shape, the angles, all of that good stuff. All right. The VSEPR theory helps us predict the molecular geometry. It helps us predict the bond angles. There's typically only the same types of angles. Tetrahedral shapes have that 109.5 degree bond angle. Trigonal planar, the 120. Linear, the 180. All right, those are the really big important ones. It does help us if we have a Lewis structure, we can predict the bond order. All right, so that's just single, double, or triple bond. And if we have resonance between two, we can divide it. So these would be 1.5, right? Halfway between 1 and 2. So that's something where if we have the Lewis structure and the VSEPR model, that's the best way because each is a little bit incomplete. The term hybridization. All right, we talk about hybrid orbitals. It's when S and P orbitals blend. All right, they come together. So typically what we see happen is the S and P's get mixed together. So that leaves us with SP, SP2, and SP3 hybridization. The important thing to remember, all right, if you take the exponents of S and P, you can add them up. That gives you the total number of bonding groups. So SP, it would be 1 plus 1. You're going to get 2 bonding groups. SP2 hybridization, 1 plus 2. You're going to have 3 bonding groups. And SP3, S plus 3 Ps, total of 4 bonding groups. For the AP exam, you don't have to worry about 5 and 6 groups. Those are the DSP3 and D2SP3. All right. Based on those hybridizations, they tell us the angles. So SP hybridization is always linear. All right, it's S and 1P being blended together. We get these weird kind of bow tie shapes, but this would represent 2 groups overlapping. All right. Then if we have SP2, you're always going to get 3 groups overlapping. It's always going to be trigonal planar, which is going to give us that 120 degree bond angle. And again, it's trigonal planar because that's what 3 shells of electrons repelling each other looks like. All right, some good examples, BF3, right? We talked about that boron, that exception to the octet rule. It has less, but that forms the 120 degree bond angles in a trigonal planar shape. SO3, important to note here, this is not an ion, right? This is a neutral compound. We get 3 triple bonds though. This is a trigonal planar shape. And carbon can form sp2 hybridization if it forms a double bond. Here, this is CH2O. I don't know what happened to my H's. They got a little cut off, all right, but trigonal planar. sp3 hybridization, 1 s orbital, 3 p orbitals. We get 4 total groups, all right? This is very important for carbon. Carbon typically is sp3 hybridized as long as it has no lone pairs, actually no double bonds. So methane, CH4 is that tetrahedral shape. Even as we change bonding atoms to lone pairs, NH3, it has 1 lone pair, it still starts out with that tetrahedral shape, but because the lone pair is just empty space, it forms what we call the trigonal pyramidal shape. All right, still 109.5 degree bond angles, but this is kind of like a hole, and H2O has 2 of those holes, so it has the bent shape. Again, its whole overall structure is based on the tetrahedral, but because it has 2 holes, we just call it this bent shape. And it still maintains that 109.5 degree bond angle. Actually, for these, they're slightly smaller because the lone pairs push them out of the way. All right, so again, carbon, it can be sp3 if it forms 4 single bonds, sp2 if it forms 2 single bonds and 1 double bond, or sp if it forms a single bond and a triple bond. It could also be sp if it forms 2 double bonds, right? And that's coming right from the MCAT review, which you need to take if you want to be a doctor. So this is important information to continue with, especially if you're considering a medical career. All right, and just again, when we look at these structures, we should be able to determine the hybridization just by looking at the number of groups around it, right? So for the CH3 and it's connected, that's 4 total groups, the 3 hydrogens and the 1 carbon, sp3 hybridized, right? For this carbon here, it's got 2 groups, the nitrogen and the carbon. The nitrogen only counts as 1 group. It does not matter that it's a triple bond, so sp hybridized. All right, and something to point out, I showed you this graphic already, but you are not expected to understand the derivation and depiction of hybrid orbitals, all right, on the AP exam. I think it's important to know, to understand, but you're not going to be asked about it directly. But I think understanding it makes it a little bit easier to apply some of these premises of VSEPR bonds and pi bonding and things like that. All right, but again, you won't be assessed in any way on these types of diagrams. The other thing the College Board wants you to know, you will not be assessed on any atoms that has more than 4 pairs of electron groups, right? So the highest you'll go is that tetrahedral shape, the sp3 hybridization. You won't have to do the trigonal pyramidal or the octahedral, and you won't have to do the variance of them based on lone pairs. So unfortunately, that means no seesaw shapes on the AP exam, no T-shape, no square pyramidal, right? All of that good stuff. That's what the AP exam says. I am always a little distrustful of that because there are a number of old questions where they do subtly allude to those. So I think it's good just to know them, all right? But again, make sure you really know SP, SP2, and SP3. All right, and then the pi bonding. Anytime we have a double bond, we call that a pi bond. All of the single bonds, it's orbital overlap, and it's these hybridized sp orbitals. Doesn't matter how many sps, but they're all the same shape, that like dumbbell. Pi bonds are when we get unhybridized p orbitals overlapping, and because the p orbital has that dumbbell shape, it overlaps on top and on bottom. This is C triple bonded to a C, so they're trying to show in the purple and the yellow 2 separate pi bonds, right? P orbitals overlapping. Typically, they go above and below the original bond. Something to note, all single bonds are called sigma bonds. If you have a double bond, one of them is a sigma bond, the other is a pi bond. It doesn't matter. It could be top, bottom. It does not matter which one's which. But every time we look at a double bond, we should think one of them is sigma, the other is pi. That's it. That's all you need to know. If it's a triple bond, one of them is sigma, the other 2 are pi. So it's either going to be a sigma bond, a sigma pi for the double bond, or a sigma pi pi for the triple bond. All right? And they can't rotate. This is something that's really interesting. If you were to build these with the ball and stick models that we've used, if you have a single stick, you can rotate the atoms. And that's something that is really developed in organic chemistry. So if you take organic chemistry next year at the school or later down the road in college, you'll see what that rotation looks like and why it's so important in carbon structures. But when you have a double bond, and it would be the 2 springs, you cannot rotate it. So we can get what we call these structural isomers. And I'm only mentioning this because I noticed it in an AP question the other day. You didn't need to know what a structural isomer is, but because they're using it as part of a prompt, I think it's good for you to be aware of it. So both of these formulas are C4H10. They're both, or H8. Yeah, H8. They're both butene, but they have different forms. So on one of them, both of the carbons coming off the double bonds are pointed downward, whereas that's the cis-2 butene, and in the trans-2 butene, one's pointed downward and one is pointed in the opposite direction, upward. So cis occurs anytime both groups are pointed in the same direction, coming off of a carbon-carbon double bond, and trans is when they're going in different directions. So it was like an equilibrium question, and it was between a cis-2 butene and a trans-2 butene. That's what's going on. Since the double bond can't rotate, these are not exactly identical. They technically have different structures. And something that the AP exam makes a point of saying, molecular orbital theory is not assessed on the AP exam. We didn't even bother learning it. I like to look at it after the AP exam. It's some interesting stuff. In some ways, molecular orbital bond theory explains bonds better than the Vesper model. All right, I really like the Vesper model, but apparently it just doesn't withstand certain scrutiny at the college level. So it's a good starting spot, which is why it's in the AP exam. But you will move on from it if you take further chemistry classes in college. You'll see molecular orbital theory, but molecular orbital theory, it's some really weird stuff. It's a whole different system you have to learn how to write out. It's not impossible, but you're not going to see any of this. Do not worry about any of this. All right. Here's a little joke about molecular orbital theory. Um, because of how complicated it is and because of how new it is, even though at that top level it explains bonding really well, I think because of the fact that it's just so different and it kind of requires its own system, that's why it's left out a lot of times. So don't worry about molecular theory. We'll see that after the AP exam in class. All right, so that's unit 2. Certainly a lot of stuff to go through, but things that you've been seeing Lewis structures all year, so you should be pretty okay with that. So I definitely recommend, do a little bit of practice with this, but you should be in good shape. I think unit 2 will be pretty good with. A lot of it is redeveloped in unit 3, the intermolecular forces. So as long as you can draw these structures really well, you should be good for unit 3 as well.